Hello, welcome to a review of Automated Order Pickup, a low-cost pickup system that integrates database tracking, barcode scanning, and robot systems to collect packages for the end user with an automated and easy-to-use system. Online orders have become much more common in the past few years. Therefore, an automated order pickup system could be a valuable tool, as it allows for less human labor, faster pickup times, and new possibilities due to robotic workers' improved capability. The main problem that the design addresses is the limitations of human labor in the distribution industry. Humans are unreliable as they are limited by their size and strength, as well as their own personal motivation and work ethic. Machines have been created with the purpose of aiding human labor by allowing them to lift heavier objects and reach places higher and faster than before. Therefore, we've designed a prototype distribution system to demonstrate the utility of a similar system. The three main subsystems of the project are the kiosk, the iPick-up boxes collection robot, or iPub for short, and the conveyor belt. The design for each subsystem was adjusted throughout the semester, so we will discuss each system in depth separately. The kiosk is designed to serve three purposes, which were divided into three tabs in the user interface. 1. Allow users to place orders. 2. Convert order identification data into instructions for the iPub. And 3. Allow system managers to adjust the database. To place an order, the user selects order contents, then the kiosk sends an email to the address provided by the user containing an image of the barcode holding the user's order information. To receive orders, the kiosk uses the host's default webcam and barcode recognition software to identify order details. The kiosk converts these order details into byte-length opcodes representing the path of movement for the iPub. The kiosk then encodes and sends the bit string to the Raspberry Pi Pico, controlling the iPub's movement using a serial connection. Finally, the kiosk's database management system allows a user to set all database values to predetermined values, change any values, view all values, and delete all data.
The package collection robot, nicknamed iPub, which is short for iPick-up boxes, is a robot capable of moving in three different axes and while also opening and closing a gripper. The x-axis, which moves the robot left and right with respect to the front of the shelves, is controlled by a DC motor that drives a timing belt. The y-axis consists of a linear actuator that moves a gripper closer to or away from the shelf. And finally, the z-axis moves the robot up and down with respect to the floor, which is controlled by using a DC motor that turns a winch system, which pulls a rope in a pulley system that lifts the gripper up and down. All of the hardware for the package collection robot, or iPub, is controlled through the use of a Raspberry Pi Pico microcontroller. The program for this microcontroller was written using MicroPython, which is an embedded systems version of the interpreted language Python, which is intended for rapid embedded systems development. Several peripherals from the Raspberry Pi Pico are critical in order to making the collection robot function as intended. The first of these being digital I/O. This provides the interface to read in states from the limit switches, which provides positioning for the robot. The digital output, on the other hand, provides a mechanism for sending the values needed to the L298N, which controls whether the motors are on or off. Another module that is critical is the PWM module. This is used to control servo positioning, as well as providing the ability to control motor speed during normal operation. The UART module for the Raspberry Pi Pico is also critical because it provides the interface between the host PC running the kiosk and the Raspberry Pi Pico microcontroller, allowing it to read commands from the kiosk. Finally, interrupts are used with Hall effect sensors in order to read the state changes for the motors in order to use this data to determine accurate motor positioning. The basic function of the Raspberry Pi Pico program reads in bytes from the kiosk, which correspond to specific commands for the microcontroller. For instance, if it receives the byte corresponding to the ASCII character L, it will move the robot left one discrete step, which corresponds to a specific number of motor rotations. The purpose of the conveyor belt in the design is to move the box that is collected by the robot to the end user for order pickup. It works by using a vinyl belt that is wrapped around two PVC pipes and uses a tensioner in order to remain taut. The driven roller is turned by a DC motor, which is connected through a shaft coupler to a wood dowel that acts as the shaft. This is controlled by the Raspberry Pi Pico in the collection robot and currently can rotate in forwards and backwards at one speed. Through the L298 and motor driver, it would also be possible to control the speed, and using the Hall effect encoders, it would also be possible to control the position to allow for precise positioning of the object. However, moving the design forward, it would be ideal to use a laser eye, such as at a supermarket checkout line, in order to detect when the box has gotten to the end of the line, so that way you can always stop the box at the same position.
According to our design specifications, the prototype must collect boxes from a 3x3 grid of 6-inch boxes. Therefore, it must, and was able to, move up to 3 feet vertically and horizontally. According to our design specifications, the system would be able to retrieve a package in under 1 minute. Two primary factors contributed to the system's performance. The components used in the design were selected for torque rather than speed, sacrificing speed for power and price, and that the robot's software cannot interpret its next instruction until it has completed the previous instruction, forcing the robot to execute one instruction at a time.
The robot was designed to take in an external 12-volt DC voltage in order to power its onboard electronics. However, the Raspberry Pi Pico microcontroller and the servo that drives the gripper were unable to operate at this voltage. The servo operates on a voltage range 4.4 to 6.8 volts, while the Raspberry Pi Pico operates at a voltage of 3.3 volts to 5 volts. This means that buck converters had to be used to step down the input voltage to a safe output voltage for these devices. LM2596S buck converters were used to accomplish this task.
The iPub's vision system, labeled as the box scanner, was a failed subsystem. The box scanner was designed to measure QR codes in less than 1 second. However, poor testing led to reliance on poor hardware that did not meet design requirements. Proper testing was conducted too late into the production timeline, which led to design changes that excluded the box scanning aspect of the vision system.
The robot had several strengths. The first strength was the raising and lowering mechanism. Through the use of the winch and pulley system, was able to lift more weight than was required. This strength makes it more applicable to an actual warehouse type situation. Also, the drive system was accurate enough to get the gripper to the boxes that it needed to. This was accomplished through the use of the Hall effect sensors in order to create accurate motor positioning. To improve the robot, the system is currently very slow in its current implementation, and implementing multitasking in the software for the Raspberry Pi Pico would be able to solve this problem. This would allow the device to move multiple motors at one time in order to allow for X and Z axis movement simultaneously, reducing the time needed to get to the desired box. More powerful and faster components could be selected in order to make it lift even more weight and move even faster. Moving forward, the rail system is rather clunky, so a better design would be a line-following robot that would be capable of operating in a warehouse environment more effectively. This would reduce the need for any rail system whatsoever and would only require a line to be painted on the factory floor to follow. The pulley system could be replaced by a more robust scissor lift, which would be able to reduce the storage size of the device while also lifting the weight required to pick up boxes. The gripper didn't work particularly well because it had issues with chattering and would drop the boxes. By doing research for different gripping mechanisms for boxes, a more reliable method of grabbing different sized packages can be created. Also, a wireless system that ties all the components together without the use of wires would make it more viable for mobile use in a warehouse. Another issue for a warehouse application would be the device is currently powered through the bench power supply. If the device could be moved to battery power, it would be more versatile and actually useful in a mobile warehouse environment.